Okay, people, we are talking today about section 4.4, and I'll let you have a second to read the comic and figure out what it is we're talking about. Clearly, we're talking about irrational numbers. You get the joke there? Because they don't make any sense. This is totally irrational. It's actually not what irrational numbers are, by the way. Obviously, you knew that. Let's talk about what irrational numbers actually are, and then we'll look at how it applies to us in math. Okay, well, we have talked about rational numbers in the past. And those are those numbers that can be expressed as a fraction m over n, where m and n are both members of the set of integers. In other words, -2, -1, 0, 1, 2, 3, all those numbers there, provided that n does not equal 0. Another way of thinking about these is that these are repeating decimals. Okay, so the decimals that stop like 0.6, or decimals that keep going on forever, 0.6666666, like that. Okay, those are rational numbers. So then irrational numbers are basically just the opposite. In other words, they just aren't those things. So you cannot express them as a fraction with integers, or they are non-terminating, non-repeating decimals. Okay, and of course, the most famous one that you're probably all familiar with is pi. Okay, pi goes on forever and ever 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 and ever. But there is a different set of irrational numbers that maybe you're not familiar with, but we've been working with this chapter. Okay? And that is all of those square roots that are not perfect squares. So for example, the square root of 1 and 4, we know those, but these ones in between, these are all irrational numbers because they are not perfect squares. So any number that is not a perfect square, if you take the square root of it, the answer is an irrational number. Okay, so if, for example, you take the square root of 4, you get 2. But you take the square root of 5, and you get a non-terminating, non-repeating decimal. It goes on forever. There's never a pattern to it. Okay, and all all numbers that are not perfect squares, if you take the square root of them, that's exactly what you get. Okay, so the square root of an imperfect square is equal to an irrational number. Okay, nice little visual lesson for you. So that includes numbers like 8 to the power of 1/5. We know 8 is a perfect cube, but does not have a perfect fifth root. So this extends not only to perfect squares, but perfect cubes, numbers with a fourth root or a fifth root. It all extends to that as well. So for the cube root of 4, for example, another example. Anyway, so just kind of we're looking now at some notation and just switching back between radical form and just the exponential form, which we're pretty much used to at this point. I want to take a little bit of a look for now at this form here and how we get there from these two numbers there. Those are terrible arrows. So any irrational number is going to be typically is going to be written as a radical like this. And there's different parts to it. First of all, there is the radicand. That's the number inside the square root or the root sign. And then there's the index, which is the number that tells you what root you're trying to find. If there's nothing written, then it's a 2, like the square root. Or if there's a 3, it's a cube root, etc., etc. So 16 to the power of 1/6 is an irrational number. And if I were to write it in radical form, I would write the radicand as being 16 because it is. Okay, but my index is going to be 6. Okay, so whatever the numerator, or sorry, the denominator is in your rational exponent, that becomes the index in your irrational number, in the radical form. Well, what about when there's a numerator that besides 1 in my rational exponent, like this? Well, okay, we've treated this as separately, as in other words, we take the numerator out, so something like this. So the cube root of 25 squared, and you know, power of a power, you multiply exponents to get you back to the original. And then in radical form, that would give us the cube root of 25 squared. But the question is, I want you to answer, is that the same as saying the cube root of 25 squared? In other words, square 25 and take the cube root. Is it the same as taking the cube root of 25 and then squaring your result? Let's figure that out right now. Okay, so on the left here, we're going to take the cube root of 25 first. So 25 and the cube root is that number there, 2.924, blah, blah, whatever, some irrational number. And then I'm going to take that result and I'm going to square it. So I'm going to go squared. Where'd my square? There it is there. Boom. Okay, 8.5498, blah, blah, blah. You can see it there for yourself. Okay, well now let's have a look at the other side. In other words, we're going to take the cube root of 625 because that's what 25 squared is, 625. So there's a previous answer, 8.5498 below whatever. Now let's do the cube root of 625. And boom, look at that, the exact same thing. So yes, they are in fact exactly the same. So that means that these two things are the same, they are equal. So when I write the number 25 to the power of 2 over 3, I'm basically saying that 3 is the index and 2 is the exponent on the number either inside the radical sign or outside, it doesn't really matter. So then 9 to the power of 4 over 3, written in radical form, is simply 9 to the power of 4, the cube root of 9 to the power of 4. And again, this numerator simply becomes the exponent there, and the denominator simply becomes the index. So then really quickly, why don't you sort of, if you can write it down or picture it in your head, what is this going to look like in radical form? And if you said the 7th root of 144 to the power of 5, you're correct. How about this one? A little trickier. I'll give you 3 seconds. Okay, well if you came up with this one, the cube root of 6 to the power of negative 2, not bad. But we can get rid of that negative exponent by doing this. Taking the reciprocal, so the cube root of 1 over 6 squared. Or if you wanted the cube root of 1 over 36, I'd accept that as well. Okay, well all this background stuff is building up to a little bit of radical math, or in other words, math with irrational numbers. But we're not going to be doing too much of it, but we'll do some very simple stuff. For example, we know that 5 times 7 is 35, but did you also know that root 5 times root 7 is equal to root 35? So in other words, if we use the same index for both of all of our numbers, the math kind of works out the same way. Okay, we're not getting into addition or subtraction, that's a bit more complicated, but just simply multiplying radicals together like that is very straightforward, so long as they have the same index. So this statement here would also be true. And if you don't believe me, you can definitely take your calculator out and check it out for yourself, but it's true. Okay, well let's look at this one. 4 times 9 is 36, which means that root 4 times root 9 is also equal to root 36. But these are all perfect squares. In other words, this is 2 because root 4 is 2, root 9 is 3, and root 36 is 6. So it works for that as well. Okay, now we're getting on to something here. How about this one? Okay, 25 times 2 is equal to 50, which means root 25 times root 2 is root 50, but one of these is a perfect square. That is this one here. This is 5. Root 25 is 5. Times root 2, we can just say 5 root 2 is equal to root 50. And what we have here, we've created two different kinds of radical. We have a mixed radical on the left because I have a coefficient, that's an integer, and then with a number in the radical sign or the square root sign there. And then on the right, you have everything underneath the radical sign. There's no coefficient. I mean, besides 1, but that one never really counts. And so we're going to spend the rest of this the rest of this video rather, just looking at how we go back and forth between mixed and entire radicals. So we're going to kind of work backwards a little bit now. So I have root 200, and I know that if I were to have to write this as a product of radicals, I could write it as root 100 times root 2. And the reason why I chose root 100 because that is a perfect square, and it has an answer 10. So root 200 could be written as 10 root 2. And so I could also write it though as root 50 times root 4, right? And that would also give me a mixed radical. That would give me, well, this would be 2 root 50, okay? But the problem is that this here is still has some perfect squares in it. This would be 2 times, and then root 25 times root 2. And so this would be 2 times 5 times root 2, which is exactly the same thing as I started with, which is 10 root 2. Okay? All I'm saying is we have to look for perfect squares that are factors of our entire radicals and pull them out to make a mixed radical. Okay, so what I want you to do is to make a list of all the factors of 24 and then see if you can find what the biggest one is that is a perfect square. Just do that for now. Okay, there are all the factors of 24. I don't think I missed any. And there is the only one that is a perfect square. Okay, and so I can rewrite root 24 as a mixed radical by pulling out that 4. In other words, by writing it as root 4 times root 6. Okay, and the square root of 4, of course, is 2. So this is 2 times root 6, or I just write 2 root 6. Okay, why don't you just take just a moment and see if you can do the same thing for root 48. Try to pull out the largest perfect square that is a factor of 48. Go ahead and try it. Okay, well, there are all the factors of 48, and then 16 is the largest perfect square. You may have pulled out the 4 again, and because you missed the 3 times the 16, it's an awfully common one to miss, but it's there. So then I'm going to pull out the 16 out front. This is going to be root 16 times root 3, okay? And then I know the square root of 16 is 4. This is 4 root 3. So on your calculator even, you can do 4 times the square root of 3, and it's the same as saying 4 times, or the square root of 48. Okay, now be careful with this one because this is a perfect cube now. I'm looking for factors of 16 that are perfect cubes. Can you do this one on your own, I wonder? 3 seconds. So hopefully you recognize that 8 is a perfect cube. So this is going to be 2 times the cube root of 2. You can do it like that. Okay? All right. That's it for today. I'm just going to give you 3 questions to do for homework. Here they are here. All I want you to do. Sorry, I lied. There's 4 questions. For the first 2 on top there, I want you to write those as entire radicals. And for the ones in the bottom, I would like you to write those as mixed radicals. And if you do those 4 questions, you will get 5 whole marks for homework tomorrow. See you then.